Today I would like to talk about another instability which is very extensively studied in plasmas as well as in fluids. It is called Rayleigh-Taylor instability. We shall discuss plasma in a gravitational magnetic field. How can you sustain a plasma in a gravitational magnetic field? The plasma electrons and ions will experience a drift called G cross B drift. Then we will discuss the physical mechanism of Rayleigh-Taylor instability. We will carry out a instability analysis using fluid theory, obtain a dispersant relation and the growth rate. Then we will discuss some applications. This instability has been found to be important in ionosphere, F region of the ionosphere, and also in a different form it has been found to be relevant, important in mirror machine and tokamak. Well, let us consider a liquid. This is a lighter liquid and on top of this there is a heavier liquid. For instance, if I put a stone on water and if in a column there is no point, no region for the water to get up and the stone exactly fits the channel, then the stone will compress the water. A stone density is larger than the water density, and if the stone is very hard, it does not allow the penetration of the water through it, then you can have a stone swimming over water, because if I have a container, like exactly tight container in which water is filled there, but a stone is just exactly fitting in here, then there is a possibility that a stone can be there. However, if there are no walls here, then water can go up from the sides and a stone will drown in water. Now consider a situation, suppose I have a lighter fluid somewhere and a heavier fluid. So this is a lighter fluid and this is a heavier fluid filling in this region. In principle, you can have an equilibrium when the upward force by the liquid balances the gravitational pull downward on the heavier liquid here. This is a heavier liquid and the lighter liquid. What will happen? Suddenly there is equilibrium possible. The issue is, if suppose there is a small perturbation, what will happen? So on the interface between a heavier and lighter fluid, if this is the interface and suppose there is a perturbation like this, then if the heavier fluid comes down somewhere, if there is a ripple in the surface, then there is a non-equality of pressure. Pressure in this region is less, pressure in this region higher, and as a consequence the gravitational force on this portion will not be balanced by the pressure alone, and this liquid will start coming down here and it will going up here. So the ripple in the surface dividing the two liquids will grow, and the liquid in those smaller deeper portions or troughs will keep on going down, and here it will keep on going up. So liquid will move up, lighter liquid will move up and heavier liquid will move down, and this situation is called unstable situation. Lord Rayleigh examined this issue, this problem, and you cannot have a stable equilibrium with lighter liquid being below and heavier liquid being on top, and this phenomenon gives rise to the phenomenon of convection. This is a conventional thing in liquids. Now we want to examine what will happen in a plasma. Is it possible to contain a plasma? Suppose there is a plasma here and there is vacuum here. but this is placed in a gravity, like ionosphere is a region of space plasma which is above the surface of the earth, so earth can pull it. So if I, well, there is no vacuum here, there is air, but suppose I have a plasma which is supported against the gravity. Gravity is in downward direction with acceleration due to gravity g. Well, if there is no magnetic field, then suddenly plasma will fall down. So suppose I create a magnetic field which is perpendicular to the plane of this paper. Then what will happen? Any plasma electron or ion, when it sees a gravitational force downward mg, and it also sees, it starts moving down, then it also sees a magnetic force which is the product of charge, velocity and magnetic field. If minus E is the electron charge, V is the electron velocity, Bs is the static magnetic field, then net force on the electron would be this plus this, and this will be rate of change of momentum. One of the possible equilibria is that velocity becomes constant after a while, and electron will acquire a velocity given by this equation, this is equal to 0. So if I put this right hand side equal to 0, you get a velocity that is called g cross b drift. And for instance, if I take g in the downward direction, let me specify my coordinate system. This horizontal direction I will take to be x, vertical direction I will take to be y, and well, I think in some literature people take y, the downward direction as the direction of gravity as y. So this is minus y upward and plus y downwards. So if I choose this situation, so g if I take in the minus y direction, then this is equal to minus m g. If I write down the y component, this term, this will be E V, this is in the z direction. So this will be y component I want, so I will this get Vx and z, but plus sign here equal to 0. This is, so when I equate the y component of this equation to 0, I get Vx is equal to m upon E Bs and g. Similarly, if you calculate for ions, Vx for the ions would be mass of the ion g upon E Bs, but sign will be opposite because charge of the ion is opposite to the charge of the electron. This is called G cross B drift because it is perpendicular to gravity, which is in the y direction, and magnetic field in the z direction. G cross B, x cross z, y cross z. Did I make a sign error of sign? Let me just check. G is in the y direction, so y component of this will be z x minus. So this is plus. This is correct. I think this is not wrong here. This is fine. I will call this velocity of electrons as V0, this Vx is equal to V0, and this velocity I will call as V0I, the ion velocity. I would like to examine if I perturb this equilibrium, what is going to happen. Please note, electrons are going in one direction, positive x direction, which is parallel to x axis, and this is parallel to minus x direction. Let me consider a perturbation in the surface. Suppose this is the boundary between the lower boundary of the plasma. This is vacuum here and plasma there. Please note, electrons are travelling in this direction. This is direction x axis. So this is V0 of the electrons, and ions are travelling in the opposite direction V0I. Sorry, arrow is here. So, ions are travelling in this direction and magnetic field is in the z direction. Z direction is where? Let me just understand this. X direction is here, y direction I am taking downwards. So, x cross y is above the paper in the vertically upward direction like this, perpendicular to the plane of the board, and this will be upwards, x cross y. No, into the plane of the television. X cross y will be a right-handed screw going to this board. Now, when the electrons and ions move in opposite directions, look at this region here, the ions will come somewhere here and electrons will be appearing there. So, when they will produce an electric field in this direction. Now, this is the electric field in the x direction, magnetic field is in the z direction. So, x cross z, if you calculate the force, the electric force will be minus E on the electron and magnetic force would be minus E V cross B. This is the net force on the electrons due to the electric field plus the velocity that is generated by the V cross B motion. So, from here calculate the value of V. This I call as the electron velocity that it will acquire because of the electric field, that velocity you will obtain from here. And if I take the balance the two, then this will give me V, which is equal to E cross B, you can just verify this, upon B square. So, what is the consequence? The consequence is that the force on this will be E cross B upon B square. Electric field is in the x direction, B is in the z direction. So, this turns out to be minus y. I am a bit surprised. The electric charge here is negative, this is charge is positive here. Sorry, in this region the electric field will be in this region, the electric field will be in this direction. Sorry, this will be where? The field will be in the minus x direction, so the force will be probably I made a mistake in the drift. If the charge is positive, this is this kind of thing and this is this way. Well, it so happens that this velocity should be the downward here and upward here. I might have made some error in calculating the G cross B drift direction, but essentially what happens is that the space charge motion, the electron and ion motion in opposite directions, when you perturb a boundary between plasma and free space, then you create space charges on the boundary and that produces a net electric field, and that E cross B drift pulls the electrons and ions together. This is independent of the charge and that pulls the plasma down in the trough direction and pulls the plasma up in this direction, enhancing the perturbation. This is called the Rayleigh-Taylor instability. So, a plasma supported against gravity by a DC magnetic field is unstable, just like a heavier fluid supported by a lighter fluid is unstable. Here a plasma supported by a magnetic field is unstable. Now, in order to carry out the mathematical analysis of this process, we will consider a simpler model. Rather than considering a sharp boundary, we will consider a diffuse boundary, a slow boundary. So, I will consider a situation that I have a density gradient in the vertically upward direction and gravity in the downward direction, and a static magnetic field perpendicular plane of the paper. So, I am considering a geometry in which G is parallel to Y I am taking y as the downward direction, and this is my x direction, and my static magnetic field is in the z direction. And I will consider a specific variation of density with distance, and I will consider to be increasing function of height. So, I will consider something like n0 1 minus y upon ln, because I am choosing y direction downwards. So, as you go up, you are going to higher and higher values of negative y. So, density will increase because y is negative, and consequently this increases. So, this just choose this. And if I do this, then let me begin with my equilibrium first. For the sake of simplicity, I will consider the plasma to be having no temperature. So, electron temperature is not there, ion temperature is not there, no collisions. I will not consider any collisional effects, to be simple. I am considering a plasma in which the gravitational force, which is minus m or the plus mg in the y direction, is balanced for ions. Like, let me write down for ions, plus E V0 cross Bs. Now, let me equate this to 0 in equilibrium. So, the value of V0 that I get, you can obtain by taking y component of this equation, mg, this is x, this is z, so minus E V0 x Bs equal to 0. I think that is the mistake I had made earlier. So, you get V0 is equal to mg, this is ion motion I am considering, so put an ion mass here, ion mass here, ion mass upon E Bs. This is the equilibrium velocity of ions, and put a subscript I here because I am correct motion ions. So, put a subscript I to characterize this ion motion. So, ion drift velocity is in the y direction, no, x direction. And similarly, if you calculate the electron drift velocity V0e, it will be mass of the electron into g upon E Bs, but the sign of charge is opposite. Please note that the electron drift velocity is very, very small as compared to ion drift velocity, because electron mass is very small as compared to ion mass, and hence this I can ignore. So, ignore this. So, this is my equilibrium, and I would like to perturb this equilibrium by a perturbation. I want the perturbation to have a k vector in the x direction, because this is like a ripple in the x direction. So, consider a perturbation of electric potential phi is equal to A exponential minus I omega t minus kx. I am perturbing my equilibrium by this electrostatic perturbation, and like to find out whether this perturbation will grow, means omega will be complex with a positive imaginary part or not. To examine that, I need to find out, I need to solve the equation of motion and equation of continuity for electrons and ions, both, and then I need to solve the Poisson equation. This I have to do. So, let me write down the equation of motion. for electrons, which is mass into delta V by delta T plus V dot del V is equal to minus E, the electric force, minus E V cross B, the magnetic force. This I have to consider. In the system there is only one magnetic field, that is the static magnetic field, which is in the z direction. The perturbation is purely electrostatic. So, electric field is minus grad phi and there is no magnetic perturbation. So, B field of this wave is 0 because curl of E is 0. Another thing, for electrons this velocity I can write down as a equilibrium velocity which is nearly 0 plus a perturbation quantity P V1. And when I substitute this here, I ignore the product of perturbed quantities. So, this term does not contribute at all, and this term survives, this will survive, this will also survive, this V1 cross Bs. So, let me write this equation for the perturbed velocity as delta V1 by delta T is equal to minus E grad phi, sign reverses, upon m minus omega c V cross z cap, where I have defined omega c as EBS upon m. E is the magnitude of electron charge, m is the electron mass, and Bs is the magnitude of static magnetic field. So, I have written that equation in this form. This is perturbed velocity. Replace delta delta t by minus I omega because phi varies in that fashion, which is the driver for this velocity. So, you get minus I omega V1, bring this term also from the left hand side, so it becomes plus omega c V1 cross z cap is equal to, right hand side will be I E k phi upon m. Write down its components, x component and z component, or y component. X component would be minus I omega V1x, this will give you plus omega c V1y is equal to I E k phi upon m, because k is in the x direction. For the y component you will get, y component equation will be minus I omega V1 y minus omega c V1x is equal to 0, because there is no y component on the right hand side. This equation gives you V1y is equal to I omega c upon omega V1x. Take this on the right hand side, divide by minus I omega, and you will get this result. And if I use this in this equation, I will get V1x also. So, V1x is equal to minus, if you just be careful, you will obtain this E k upon m omega square minus omega c square into omega up here, because 1 omega was there. So, you just obtain this, you can just verify this, minus E k phi upon m, this expression you will get. For this wave, if omega is much less than omega c, which indeed it is, then this is approximately equal to, ignore this, you will get minus E k omega phi upon m omega c square, and sign becomes positive. So, electron density perturbation, velocity perturbation is simply this expression. And let me calculate the density perturbation also. The density perturbation turns out to be, can be obtained from the equation of continuity, delta n by delta t plus divergence of nv is equal to 0. N expressed as n0 plus n1. Use this here and linearize, you will get delta n1 by delta t plus n0 del dot v1 equal to 0. Replace del by ik, sorry, I made a mistake here. N0 is not a constant quantity, this is wrong. So, let me delete this is not right. Remembering that N0 depends on y, it is increasing in the vertically upward direction. N0, please remember, is equal to N00 1 minus y upon ln. Sorry, I made a mistake, N0 should be in the interior. I will get delta N1 by delta t plus divergence of N0 V1 equal to 0. This equation, please remember, N0 depends on y and V1 depends only on x. So, this will have two terms, and this is I can replace by minus I omega, because perturbed density will vary, perturbed quantities are all vary as exponential minus I omega t minus k x. But N0 is not a perturbed quantity, it does not vary in the same fashion. So, N1 V1 they go as this, but not N0, that was the error I was going to make. So, for perturbed quantities delta delta t can be replaced by minus I omega N1, and that will give me two terms here plus delta delta y of N0 into V1y plus N0 into delta delta x of V1x, and this is equal to 0. Delta N0 by delta y, if I evaluate, is like 1 upon ln into N00. So, I will just write this as 1 upon ln into N00, and that gives me how much? N1 is equal to 1 upon I omega, and here you are going to get minus 1 upon ln into N00 V1y, this term, and this will give me ik into N0 V1x. When I have taken these terms on the right hand side, this is the kind of equation I get. So, density perturbation for electrons I have obtained. Now, I will put the values of V1y and V1x, and we obtain, if I put the value of V1y, let me just write this, N1 is equal to 1 upon I omega, within this will be minus 1 upon ln N00, and this is I omega by c, omega c by omega rather, into V1x plus ik N0, N0 I can write directly as N00 of the order of into V1x. And I can take, if I please note here, k is bigger than 1 upon ln, but omega c by omega is the additional factor that comes over here, which is really very huge. Omega c by omega is maybe 6 to 10 orders of or 8 orders of magnitude for some reasonable parameters of ionosphere, for instance. This is a huge number. So, usually this term dominates over this term, but let us retain both these terms and put the value. So, what you get is 1 upon I omega, N00 I will take common. So, I put N00 out, and you will get minus I omega c upon omega ln plus I k multiplied by V1x, whose value turns out to be E k omega phi upon m omega c square. This is the dominant term actually in this expression. This is my perturbed electron density. Then I must calculate the perturbed ion density. So, for the ion response, I have to retain the effect of V0 because the DC drift is there. So, for ions, my equation of motion will be different. This is m delta V by delta t plus V dot del V is equal to this ion motion. So, put I subscript everywhere, I here, is equal to E minus E grad phi. This is the ion charge plus E, and minus grad phi is the value of the electric field, minus plus E V cross B, the magnetic force. So, when you solve this equation, put ion velocity is equal to V0 ion, the equilibrium velocity which was in the x direction, plus a perturbed quantity V1I, and use this in this equation and linearize this equation. Well, I forgot to write one more term here, that is the plus mg term. Sorry, let me write down this here, mass of the ion and gravity. This term should be written there. When we substitute this here, the V0 cross Bs term exactly cancels with this term. So, gravity does not really play any role in the perturbed velocity equation, because V0 cross B exactly cancels with this by definition. And this equation linearization gives delta V1I upon delta t plus V0 I dot delta delta x of V1I is equal to minus E gradient of phi, and this term will give you E plus E V1 of ion cross Bs. This equation we have to solve is simple. Replace delta delta t by minus I omega, delta delta x by I k, this by I k, and then this equation take the following form: minus I omega, I made a mistake, I must put a ion mass in the denominator because this mass I am dividing. This equation becomes minus I omega V1I minus V1I cross omega c I, ion cyclone frequency. I think I made a mistake over mass here as well, there is a mass there also. So, what you get here is right hand side of the equation of motion becomes minus E upon mi I k phi. This is prime here actually, and omega prime is equal to omega minus k V0 I. So, this is the only modification. This is the same equation as electron equation of motion, with charge of the electron replaced by ion charge. So, minus sign is there, electron mass replaced by ion mass. Omega Ci is the ion cyclone frequency, which is defined as EBS upon Mi, and omega prime is some sort of a Doppler shifted frequency of the wave of perturbation as seen by the drifting ions. And you can simplify this to obtain V1I y, which turns out to be equal to minus I omega Ci upon omega dash V1x of the ion, and V1Ix, rather the same thing, is equal to x component of V1I turns out to be equal to minus E k omega dash phi upon m I omega Ci square. This is what you get. So, the ion velocity perturbation has primarily omega replaced by omega prime, which is the Doppler shifted frequency of the perturbation as seen by the ions. Then I go to solve the equation of continuity. The equation of continuity also gets modified. For the ions, the equation of continuity is Ni by delta t plus divergence of N0 V1 of the ions, plus there should be a term here plus N1 perturbation of ion density into V0. This is N1I. Please, what I have done here is actually Ni I have written as N0I plus N1I or Ni1, whatever you call. So, when I substitute this in the equation of continuity, delta N0 by delta t is 0. So, this is the only term that survives, and because I have already written velocity as of the ions is equal to V0 of ions plus V1 of ions. So, you get two terms here. This is the additional term that was missing in the electron equation of motion, and the consequence of this is that del, this is a perturbed quantity. So, when you operate this with del operator, it will be replaced by Ik. So, this N1 and this N1, they will combine together. Actually Ni1 is the same thing as N1I. By mistake I have written this like this. So, this term and these two terms combine together to give you minus I omega prime into N1I. This is the means replace this by minus I omega, this del operator operating over this term by Ik, and you will get this simply omega prime, and this is equal to minus this term taken on the right hand side, divergence of N0 V1I, which again will have two terms, minus del operating over N0 first, then this quantity. So, which is equal to delta N0 by delta y, N0 of ions, the same thing as electrons also, into V1 I y, because if I take y component of this, then y has to be there, and then they will get a term plus Ik, which is the x direction. So, N0 of ions multiplied by V1 Ix. So, I will substitute the values of V1I and V1x, etc., and the result that I will write is this, is very similar to the electron result with omega replaced by omega prime, and it turns out to be N1I. Let me write down N1I is equal to N00 upon I omega, within the bracket is, so omega is omega prime, and this is plus I omega Ci upon omega ln plus Ik, then Ek omega dash phi upon mi omega ci is square and sign is opposite. This expression I have written from the electron expression, replacing omega by omega prime and electron parameters by ion parameters, charge and mass, a similar expression. After I have obtained the perturbations in density of electrons and ions, it is simple to obtain the dispersion relation by using the Poisson equation, which turns out to be divergence of D is equal to rho. This is the Poisson equation. When I substitute D is equal to epsilon 0 E and E as grad phi with a negative sign and rho, which is the charge density of electrons and ions together. So, this is equal to N0 I plus N1 I, this is into E is the ion charge density minus N0 of the electrons plus N1 of the electrons into E. Since N0 and N0 I are equal, this is equal to N1 I plus N1 into E. Sign is opposite minus of this. So, use this in here. This equation takes the following form: del square phi is equal to 1 upon epsilon 0 N1 minus N1 I. Again replace this del square by k square minus k square, and you will get minus phi or plus phi is equal to minus 1 upon k square epsilon 0 N1 minus N1 I. Just substitute the values of N1 and N1 I. You will recognize that they also contain phi, and every term that you get in N1 and N1 I is much bigger than phi. This is coefficient of phi is 1, there will be phi on the other side also, but the coefficient of those terms is much bigger than 1. Hence, I can ignore the term on the left hand side. So, this equation gives me that N1 is nearly equal to N1I, because the individual terms on the right hand side are too big as compared to unity or phi on the left hand side. So, I can ignore the left hand side term, and in order to satisfy this equation N1 is nearly N1I, and these perturbations I have already obtained. So, let me write down the expressions N1 and N1I, and what you get is this. I just write down the expression. I think it will be useful. Please note, I am to divide those expressions by epsilon 0, and I will introduce a quantity called plasma frequency as N00 E square upon m epsilon 0 to the half, where m is the electron mass. Similar quantity for ions I can define as N00 E square upon mi epsilon 0 to the power half. Then what you get when I put N1 is of the order of N1I, you can write down these expressions as follows: N1 is nearly equal to N00 E k square phi upon m omega c square minus E k phi N00 upon m omega c ln density scale length, and n1I is equal to minus n00 E k square phi upon mi omega ci square minus E k phi n00. I think there is one omega also here in this equation, omega is there, and so omega prime here, mi omega ci ln into omega minus kV0 of ions. This is what you get. The expressions are very similar and you have to equate them. Once you equate them, you get a simple dispersion relation because phi will cancel out from every term. So, n1 approximately equal to n1I leads to a very simple dispersion relation which says that omega minus kV0 of ions multiplied by omega is equal to a quantity minus alpha square. This is the simple dispersion relation. By equating these two you get, and alpha square turns out to be equal to V0 ion upon density scale length into omega p I square that I have defined earlier upon omega ci into 1 plus omega pi square upon omega c square ci square. And there is no under root. I do not think there is any under root. And this turns out to be, if I put the value of V0I as g upon omega ci, and if I, in most plasmas omega pi is much bigger than omega ci, so one can be ignored, and then this turns out to be simply g upon ln. G is the acceleration due to gravity and ln is the density scale length. So, please note your expression, the way the dispersion relation becomes omega square minus omega kV0I plus g upon ln equal to 0. A very simple dispersion relation you recover, and I find if I can find the roots, this will give you omega is equal to half kV0I plus minus under root k square V0I square minus 4 g upon ln. Well, this quantity could be bigger than 1, positive or negative. When this is positive, omega is purely real and there is no instability. So, for large values of k, this quantity is positive and there is no instability. Means if your ripple on the or the perturbation in the plasma has a small k, a large k, then there is no instability. However, for kV0I less than 4 g upon ln under root, whenever this quantity is less than this, omega is complex. And one of the roots will have a positive imaginary part. One root has positive imaginary part. And that gives the instability. So, especially when k tends to 0, means when this quantity is negligible as compared to this, the growth rate is simple because you can ignore this term, you can ignore this term, and this growth rate turns out to be. So, for k tending to 0, omega is simply equal to I times gamma and growth rate is equal to under root of g by ln, or time period of growth is under root L by g, just like a simple pendulum. This is the interesting part of it, that situation is very complex. It is a plasma with electrons and ions moving and magnetic field stopping the plasma to fall down against gravity. Still the expression is very simple, very similar to what we get in a simple pendulum. And if k is not 0, for finite k, what you get, the growth rate is, as I mentioned there, growth rate is equal to under root of 4 rather g upon ln minus k square v0 I square by 4. And please remember, v0 I is the ion drift velocity, which is equal to g upon omega ci. So this also depends on g, but k is the primary thing here. It will be useful to plot growth rate as a function of k v0 I. Normally people plot this upon this growth rate, well, some number, you will get this kind of behavior. Now this instability is important in F region of the ionosphere, and it gives rise to fluctuations in density perturbations of the order of with wavelength k of the order of, from here, g upon ln into 4 upon the under root of this quantity into 2 upon v0 I, and that turns out to be typically of the order of a kilometer. So in the ionosphere, people have observed density fluctuations with a scale length of the order of a kilometer, maybe half kilometer to 3 kilometers or so, in that range, and they are attributed to this relative instability. People also give this a name as spread F instability. Well, here I have ignored the effect of collisions. If you include the collisions of electrons and ions, then this growth rate is slightly modified, but primarily the physics remains the same, mathematical treatment remains the same, and this growth rate, this instability has been observed, always observed in ionosphere. At times people have observed very great depression in densities, especially during the sunset. People have observed order of magnitude reduction in electron density because of this density. So, but that requires little more complicated physics. It is not simply this, I have discussed the linear stage of this instability, that this instability will grow and it will cause a perturbation. And however, what happens, that you may ask a question, that if the ionosphere is unstable to this instability, the plasma should fall down. Obviously plasma will fall down, but then the air, neutral air, will go up, and again this will get ionized. So this is a dynamic equilibrium in the presence of the sun. That is why there is not a really fall down in that sense. Plasma is coming down, gas is going up, and some sort of a equilibrium electron density is maintained in the ionosphere. But these fluctuations are certainly there, and they are responsible for causing scattering of radio waves. And a lot of work on this has been done in last several decades, and it continues to be important. I may also mention that in the equatorial ionosphere there is a current called electrojet current. There is an electric field. Just like G cross B drift can cause instability, E cross B drift also causes an instability, which is similar to relative instability, and that has also been observed. That gives rise to shorter wavelength fluctuations. And I think with these two instabilities, we can understand a lot of phenomena in the ionosphere. I would like also to mention that Rayleigh-Taylor instability of late has been found to be very relevant in laser driven proton acceleration. People employ lasers to accelerate ions. For that they take a very thin foil of submicron width of a metal and shine laser on this. The laser pushes the electrons via the ponderomotive force or radiation pressure force, and when the electrons are pushed, they pull the ions also along with them. But it has been found that if there is a ripple in the surface of this foil, then if the foil takes this form, then the radiation pressure which is falling in here is different than here. The reason is that this is curved. When the laser foil, this aluminum foil or material foil is curved, the radiation pressure force exerted is different positions. The positions like these, they have acquire a larger radiation pressure force and these regions less, and consequently this foil acquires the shape. So, the perturbation grows, and this is also known as Rayleigh-Taylor instability, and I think it is one of the major concerns in laser driven proton acceleration at the moment. And I think if time permits, during our course of lectures, we will have some discussion on laser driven proton acceleration and the relevance of Rayleigh-Taylor instability in there. I think I close at this point. Thank you very much.